Okay. So I set all this up before I started this stream, but look at all those great diffuse lighting. Isn't that amazing? Isn't that absolutely spectacular? Look at my mic. Look at my Mac, which I don't know. So 0 people know this, but it's decaled with Fematika now. And I also have some more Fematika stickers in my drawer. Oh, dang it. Oh! Oh! Alright. Wait, if I can find them. Yep, there. Fematika stickers. I might be giving those away. I might be doing challenges or something, but maybe not. There. Have to plug this one back in. Uh, uh, uh. Is it gonna plug in? Please. Please plug in. There it is. Okay. Also, I have this thing, and you can see how I'm recording this. Anyway, I'm gonna show you how my videos are made. Hello. Let's get really close and on my eye. Anyway, I'm gonna be making a video for black pen, red pen. So this is a black pen, red pen video that I'm going to be making. Now I just have to pull up the notes he gave me, because he gave me notes. So once I do that, we can get going with the video. Now usually, I would put it up onto the board over there, but I don't want to do it for this, because it's just like complex numbers. Oh, okay. There we are. Scroll up. Where the heck is his... Oh, come on. Where the... Okay, there it is. There's his notes. Hey, I have a quick question. How would you, how would I... Oh, shoot. Hey, I have a quick question. How would I put the following in a mathematical statement? There exists a real number which is neither positive nor negative. So you would say backwards capital E, X, and element... let me just write it out. Okay. There exists X, an element of R, such that X is bigger than 0 and X is less than 0. Oh, shoot. Such that, not that, X is not, and not there. There you are. That's how I'd put it. Alright, anyway, we have to get to the black pen, red pen video I'm making. Just the maths. Slides numbers 6.6, complex number 6, complex loci by A.J. Hobson. The directed line segment joining the point representing a complex number z1 to the point representing a complex number z2 is equal to length. Okay, I already read over the notes, so I'm just not going to read them for you. I might put them into the chat just so you guys can look at what I'm using for the notes. Oh, that's got to be annoying seeing that. That looks like a really annoying angle. But there you go. those are the notes I'm using. Okay, let's start making the video. So it's about complex loci. Hello, pastels. I don't know how to pronounce that. And if there is a pronunciation that's correct, please tell me. I have to clean my glasses now. Oh, thank you, M322. I appreciate you, M322. Oh, that sounded really loud, but it didn't hurt, trust me. Shoot, I just realized. Okay, get out my glasses cleaner. Do you wear contacts sometimes? I don't own contacts, so no. Just my glasses are for farsight. I want to wear them for videos now. That's gonna be my thing. I used to not do that, but in order to see that board, I have to wear my glasses because it's too far away for my awful far vision. Oh, some specks on it. That's annoying. Okay. Oh, come on. I have some liquid cleaner, but I don't want to use that because I'm lazy. All right, are we good? Yes, we're good. Okay, so now I can start the video. Now, someone in the chat, tell me what the intro should be. This is going to be recommended by Black Pen Red Pen in one of his videos. So tell me what the intro should be. What exactly is the Planck time link? I'm an author for that. I'm an author for... Oh, not what the video is about. What the intro should be. So, like, should I do some funny ha-has? Just send out recommendations for the intro, not the actual contents of the video. The video, I have the notes up. I have the notes up for the video. It's on complex loci, which isn't very hard, but I'm going to do it anyway. Alright, let's fix my hair. Wow, look at how cool I look. Emulate Flammable Math's intro. You'll like it. Good morning, fellow mathematicians. Except I have to do it in his, like, weird German accent. Good morning, fellow mathematicians. That sounded not like Flammable Maths. I don't know how to imitate Flammable Maths. Good morning, fellow mathematicians. I sound like I'm making him... Okay. Let me get a reference. Flammable Maths. Let's just click on that.
I've got everything. You name it, I have it. Ligma.
Okay.
Good morning, fellow mathematicians. Wake up.
Good morning, fellow mathematicians. Good morning, fellow. Good morning, fellow mathematicians. Wow, okay, I have to emulate it.
Good morning, fellow mathematicians.
Good morning, fellow mathematicians. Okay. Good morning. How does he... Like, there's this weird... Like, he says his R's...
Good morning, fellow...
Morning. Good morning. Good... does he say, like, it's soft at the end? There's something wrong with the way I'm saying morning.
Good morning, fellow math...
Good morning? Good morning. Good. That sounds like Irish. Good morning, fellow. Good morning, fellow. No, okay, it doesn't matter. I'll just do it. It's too hard. Yeah, you're right. It's too hard to do German. Where the heck did I put? There's my marker. All right. You guys are not hearing through this mic. This mic's going straight to my laptop, which you guys are not seeing. You guys are on my phone, so I can move my phone around. And for everyone new, there are Fematika stickers that I might be giving away, but they'd have to be US only because I can't do international shipping, because international shipping's too hard. Alright, and there's probably a little known fact, but there is a tiny little stool that I can sit on over here. It's not really sitting, it's like too tall to sit on, but I can sit. That is something I can do. Many of you probably didn't know that. Alright, so I'll go ahead and do the good morning, fellow mathematicians. That sounds awful. Good morning, fellow mathematicians. That sounds bad. That sounds even worse. I can't do it. I can't emulate flammable math. It's too hard. What does Black Pen Red Pen do? Like, he has variable intros, doesn't he? But let's just go with how he did the last one. Black pen, red pen. Black people meet commercial? That's number 2. Just do it American, man.
Okay, we are going to find the derivative of e to the negative 2x times.
Okay. Okay. I'll just do it American. Good morning, fellow mathematicians. Good morning, fellow mathematicians. It sounds weird when I do it myself. When Flammable Maths does it, it sounds like, wow, I could really get behind that. But when I do it, you're just like, that's some stupid little idiot kid who everyone hates. Good morning, fellow but there's something weird about fellow as well. Good morning. Good morning. All right. Let's just... Good morning, fellow mathematicians. Okay, keep giving me ideas for the intro. Depending on the time of the day you are filmed, be like, good afternoon. It's nighttime where I am. Good evening, fellow mathematicians. In this video. So it'll be a combination of our two intros. That could work. Okay. Let's get to recording. Also, I always edit out the parts where I drop my marker, but I do drop my marker pretty often in my videos. Just in case you guys wanted to know. Okay. My hand's already sore. I don't know how Black Pen Red Pen holds the ball for like 30-minute videos. Actually, I held this for an hour-long video. Wait. Yeah, I think if I ever do a Patreon, what I'll do is I'll send out the unedited videos so you guys can see, that people who give me money can see all the mistakes I made in my original video. That'd be fun. But I don't know if I'm gonna do Patreon. That seems a little weird for me. And the other weird thing is that before, I used to use my Mac webcam, and so I'd always look at my Mac webcam when I was speaking to the viewer. But now I have to look at this webcam, which is over here, as opposed to my Mac webcam, which is over there. Now it looks weird. Guten Morgen, liebe Mathematiker. I'm gonna butcher that. I don't know. I can't emulate anything German. Do not mistake me for Einstein. Okay. Okay. Let's go. Guten Morgen, liebe Mathematiker. Okay, I butchered that. No way I said that right. Well, let me look up Guten Morgen. Say it in Spanish. Buenas tardes, amigos. Would that be it? Matematicos. Would that work? Do it in German. Guten Morgen. Guten Morgen, liebe Mathematiker. Guten Morgen, liebe Mathematiker. Let me listen to how it's pronounced. To English.
Guten Morgen, liebe Mathematiker.
Guten Morgen, liebe Mathematiker.
Guten Morgen, liebe Mathematiker.
Should be lieber. Okay.
Guten Morgen, lieber Mathematiker.
Guten Morgen, lieber Mathematiker. Guten. That's gonna be so weird doing an intro that says that. Guten Morgen, lieber Mathematiker. He's gonna make fun of me for that, guys. Final of Math is going to demolish me if I do that. But I think that's actually a good thing, because then I can get the drama points on YouTube. Shoot, it's uneven. It was even before. Now it's pretty even. Hello, fellow mathematicians. Welcome back to another Fematika video. No, I'm keeping the in this video. I just wanted like a stupid thing to do before I started it. So I'll do Guten Morgen, lieber Mathematiker. Care. Okay. Let's start it. I've spent 20 minutes just figuring out the intro. I have to turn down the sensitivity. Just so that the quality is better. Mathematike.
Guten Morgen, lieber Mathematiker.
Guten Morgen, lieber Mathematiker. Okay.
Guten Morgen, lieber Mathematiker. Guten Morgen, lieber Mathematiker.
Guten Morgen, lieber Mathematiker. That's gonna be so weird. No, lieber makes more sense. Lieber.
Guten Morgen, lieber Mathematiker.
Lieber Mathematiker. Okay. So liebe makes it plural. Okay, liebe.
Guten Morgen, liebe Mathematiker.
Liebe. Guten Morgen, liebe Mathematiker. In this video, that's gonna be so weird. Alright, I'm gonna put this in the description that you guys made me do this. Okay. Also, I should probably look at the notes. Have the notes up. Okay. So wait, was lieber correct? Or liebe? Liebe. Guten Morgen, liebe Mathematiker. I have to do that again. Let me listen to it.
Guten Morgen, liebe Mathematiker.
Guten Morgen, liebe Mathematiker. Liebe. Okay. Guten Morgen, liebe Mathematiker. Yeah, no, I don't have a wig on me. Obviously, I don't. Okay. Let's go. Let's start the video. Guten Morgen, liebe Mathematiker. Screw you, flammable maths. Screw you. Anyway, in this video, I'll be introducing complex loci, and, shoot, I forgot what I was doing. In this video, I'll be introducing complex loci and some stuff about complex magnitudes and arguments. I have to redo that. In this video, I'll be introducing complex arguments, magnitude, and loci. So first of all, let's introduce complex magnitude. So if I have some random point in the complex plane, so this is the real part, this is the imaginary part. And let's say I have a plus bi, just some random point a plus bi. The real part, I can project down. So this right here is the real part a. And then the complex part, I can project out like that. That's the complex part b. Now, the magnitude, obviously, is going to be the distance between the origin and that point. So we draw a line like that. And then we have this right triangle right there. This distance right here is the same as this distance right here. That we're going to use that fact. All right, so if this distance is b, because that's the measurement right there by the fact it's a plus bi. So this length right here across the rectangle is also b. And then this length right here, by the fact that that right there is a. So we have an a by b right triangle, and we want to find this side of the right triangle. So we have two legs of the right triangle, and we want to find the hypotenuse, which is, you guessed it, Pythagorean Theorem. So we do a squared plus b squared equals c squared, which means that c is plus or minus, but it can't be negative, so it's just the positive square root of a squared plus b squared. And that's what the complex magnitude is. So the magnitude of, and we write this with two lines, and we encapsulate it. It's like an absolute value, except we added one more line on each side. So the magnitude of a plus bi is the square root of a squared plus b squared. And that's just the Pythagorean theorem. And then something called the argument of a complex number is really the angle on the unit circle of that point. So if I have complex plane, I have some point a plus bi. Then whatever this angle right here is, that is the argument. So it's that theta. Which, if you draw out another right triangle, this is a, this is b, then I can solve for that angle. It's tangent inverse of b over a. So that's the argument. So that's tangent inverse of b over a. And that's just simple trigonometry. Oh my god, trigonometry. And that's just simple and that's just simple trigonometry. Alright, now what is complex loci? Wait, no, I shouldn't do complex loci yet. I'm going to explain more about this. Now this angle could theoretically be any number, but because we have it equal to tangent inverse of b over a, this bounds theta to be between negative pi and pi. Actually, it's between negative pi over 2 and pi over 2, which is not all of the, it's just the positive. Because if both of them are negative, then it goes back to the positive. Oh yeah, I reached this problem before. So I'll go ahead and explain that right now. So tangent inverse restricts this theta to be between negative pi over 2 and pi over 2. So, meaning which means that it's only the positive half of this complex plane. Now, to get the negative half, what you have to do is do tangent inverse of b over a plus pi over 2. So when b is negative, you have to add pi over 2 right there. That's to get it into the correct quadrant. And technically, you'd have to subtract negative pi over 2 when a is negative. You'd have to subtract normal pi over 2. So if a is positive and b is negative, so it's in this quadrant, what you have to do is add pi over 2 to tangent inverse of b over a. And if the point is in this quadrant, you have to subtract pi over 2 of this value. Sorry, it's actually add pi. Yeah, it's add pi. And if your value is in this quadrant, you have to add pi to this. Oh, shoot. Yeah, no, you just add pi to either of them. And so if it's in either the second or third quadrants, you have to add pi to tangent inverse of b over a in order to get the correct value of theta. So it's not just simply tangent inverse of b over a. That was an oversimplification. All right. Now let's talk about complex loci. So complex loci is the set, so that I use curly brackets for sets, of all complex numbers. We usually write z is an element of the complex numbers such that yada yada yada. So this is all complex numbers that have a certain property. That's complex loci. So for instance, I could do the set of complex numbers such that their magnitude is equal to 1. What does this look like? So we have the complex plane. We have all points who are 1 away from the origin. So we have 1, we have -1, we have I, we have negative I. I drew that very, very poorly. All right. Now you might already know what this is. The set of points that are an equal distance from the origin is just a circle. So this is the circle of radius 1. So that's the unit circle. This locus of points of the magnitude of z is equal to 1. And we can actually do some translation. And you might remember this from, say, pre-calculus. If you have the magnitude of z minus z naught, where z naught is some constant, and you have that equal to 1, then you translate this circle to be centered around whatever z naught is. So if right here is z naught, then you'd have the unit circle around z naught, except I drew that very poorly. It's centered around z naught. So center's more like there. So there's the unit circle around z naught is given by the locus of points which satisfy that. And now the other thing we can do is take the locus of points setting their argument, their angle, to a constant. So if I have the argument of some value is equal to, say, pi over 2, what would I get? Say pi over 4. What would I get? Well, we have all the points, which is an angle theta, which is an angle of pi over 4 from this positive x-axis. So right here is the angle pi over 4. Then all points, which are pi over 4 away, looks like this line, going like that. And now this line doesn't extend back. It does not go backwards like that, because, and the reason why this is a ray and not a line is because if I were to extend it going back, you can tell that given the fact that I defined the argument to be a different value for these two quadrants, that means that this angle right here is actually that angle, which is not pi over 4. So these points don't count. And then you can do a similar thing with recentering it. So I could have done an argument of z minus z naught equals pi over 4. And it would translate it so that it starts at z naught. So if this is z naught, boom. And that is at an angle of pi over 4 right there. So it creates the ray extending out from a point z naught at an angle of pi over 4. And this creates a circle of radius 1 centered at z naught. And then, of course, we can generalize this. So if I have the magnitude of z minus z naught equals r, this is a circle of radius r. And if I have argument of z minus z naught equals theta, where theta is fixed, this is a ray of angle of theta centered at z naught. So complex loci, the set of all points which something, are actually interesting and create all the curves we'd look at before. And I mean, of course, you could do something like the set of all points z such that the set of all points z such that the distance between z and shoot, what was I gonna say? Shoot, I was gonna say something, but I think I lost that thought. Doesn't count. Alright, what was I gonna do next? I was gonna do a more complicated example. That's right, okay. Now I'm going to do some fun facts about the complex magnitude now. Now, using the complex magnitude, I can define a distance function between 2 points, z and w. And it will be defined to be the magnitude of z minus w. And it's that easy. That's how we define distance. And that makes sense if you remember how complex addition works. You have some z and you have some w. Then their subtraction is the complex number where it's this right here and it's translated down. So, like that. So it's the magnitude of that subtraction, of this right here. And obviously, that right there is going to have the same magnitude. And obviously, that right there is the distance between w and z. And obviously the magnitude of that, by the fact that it's the same size as that, is the distance between w and z. So that makes sense for the distance. And so what we did before with the magnitude, which was magnitude of z minus z naught equals r, can really be written as the distance between z and z naught is equal to r, which sort of makes more sense as to how that's a circle, rather than it's a translation, it's actually the circle. And a fun fact about magnitude is that if you multiply two complex numbers in here, then you get the magnitude of one times the magnitude of the other, which I'm going to prove right now. So if I have the magnitude of a plus bi times c plus di, what is that equal to? So I have that magnitude. Let's do the product out. So this is equal to magnitude of AC minus BD plus AD plus BCI, which is equal to the square root of AC minus BD squared plus AD plus BC squared. Because the real component is AC minus BD, that's the stuff that doesn't have the I, and AD plus BC is the stuff with the I. Alright, if we do this out, I get A squared C squared minus 2ABCD plus B squared D squared. And then we add on to that. So this right here is just simple foiling of that. Then this right here is going to be A squared D squared plus 2ABCD and then plus B squared C squared. Now that right there is just simple foiling of that. Now 2ABCD minus 2ABCD cancel each other out. What do we get? We have the square root of A squared C squared plus B squared D squared plus A squared D squared plus B squared C squared. Oh, look at that. We have an A squared there, we have an A squared there, we have a B squared there, we have a B squared there. Let's go ahead and group that. So I have A squared times C squared plus D squared, because A squared with the C squared, A squared with the D squared. And then plus B squared, there's a D squared, and there's a C squared. Ah, look at that. Now we can group it again. So it's the square root of C squared plus D squared, and the two things it has is A squared plus B squared. Look at that. And that's equal to, because these are both positive real numbers, we can separate these out into their own square roots. So C squared plus D squared times square root of A squared plus B squared. Oh wow, look at that. That's the magnitude of C plus DI times the magnitude of A plus BI. Right? Just from the definition of the magnitude. And so that's the long approach to proving that the magnitude of the product is the product of the magnitudes, but it was sort of necessary for my next example, which is the magnitude of z minus 1 over z minus 2 is equal to 2. Let's just do that. This is a basic example. And because division is just glorified multiplication, I can just do magnitude of the top over magnitude of the bottom, assuming z is not equal to 2. That's just to make sure that the denominator isn't 0. So that's equal to 2. So I have the magnitude of z minus 1 equals 2 times the magnitude of z minus 2. Alright, let's use the definitions of magnitude and prove what this... Now let's go ahead and use the definition of... Now I'm going to use the fact that this is a circle and that this is also a circle. In theory, if I set this equal to some constant r squared, then it'd be a circle. So what I could write this as is x minus 1 squared plus y squared. This is because this is a circle centered at 1, and 1 is completely real, and so the x is 1, plus y squared. There's no imaginary part. There's no imaginary part to what we're subtracting here, and so we don't have to worry about the y squared. And when dealing with the circle equation. So this is the circle for this one, except we're not going to set it equal to a radius. We're going to set it equal to 2 times, same exact reasoning here. We're going to have an x minus 2 squared, because the 2 is the real part of what we're subtracting here. So it's centered at 2 on the x-axis. And then plus y squared, because there's no imaginary part that we're subtracting. Alright, So here we get, just FOIL that out, that's x squared minus 2x plus 1 plus y squared equals, right there, let's FOIL it out, x squared minus 4x plus 4 plus y squared. Now I get x squared minus 2x plus 1 plus y squared equals 2x squared minus 8x plus 8 plus 2y squared. Now if I subtract off y squared there, x squared there, I get x squared minus 8x plus 8 plus y squared equals minus 2x plus 1. That's just simple subtraction by x squared right there, and subtraction by y squared right there. Alright, then I'll add 2x to both sides, and I'll subtract 1 from both sides. What do I get? I get x squared minus 6x plus 7 plus y squared equals 0. Now I'm going to complete the square on this one. So that's x squared minus 6x plus, you can do this out, it's going to be plus 9 plus y squared. And because I added 2 on this side, from the 7 to the 9, I added 2. So I have to add 2 to that side. And so I get x minus 3 quantity squared plus y squared equals 2. Meaning that this is equivalent, so this statement right here, of the magnitude of z minus 1 over z minus 2 equals 2 is equivalent to the magnitude of z minus 3 is equal to the square root of 2. Right? That is the equivalence between these two things. Very, very cool how even though this clearly shouldn't be a circle, but we still get a circle out in the end. Okay, this is a 20 or so minute recording right now. And you can do some similar stuff with argument. But I think the video is long enough already, so I'm just going to stop it there. And that's it. Oof. Oh, God, my wrist. Every time I get done with the recording. Whew. Ugh. Alright. Now I have to edit it. Except I'm not going to do that today. Maybe not. I usually don't do it on the same day. Comp loci. That's what I'm going to save it as. Oof. Ooh. Ooh, wow. My hand does not like that feeling. Okay, now I also have to record a specially asked video, except I completely forgot what it was about. Tensors. Tensors, yeah. So I'm just gonna skip. What do you mean you didn't get a thing I did? It's complex because I do 7th grade math. Oh, why are you on my channel? How did you find it? How did you find my channel? Oh, God. Whew. Oh, who's your friend? Are they, like... Who's your friend? Do I know them? Do they know me? Are you a real life person that I would know? Did they have an answer? Do I not? How did your friend find out about me? Oh, he just like, okay, I got it. Alright. So I'm going to be skipping. Oh no, I should make it a wrap it up on tensors. So it's going to be a nice quick video, hopefully. Oh shoot, my phone's low on battery. Not good. Also, everyone, join my math Discord server. It should be in the description, the invite link to my math Discord server. So that's where you can get all of your fun old math. Okay, Zeptatology says, oh boy, he lived. Because I am a Christian man, I do not swear. Ugh, okay. Well, I'm going to do a wrap it up on tensors now. So, I think I'll start off. I'm vote for Aiden. Very nice, Zeptatology. Very nice. Thank you for joining my Discord server. Can you please preach how great our Discord server is to the rest of the people? Okay. We have to do tensors. So, thank you, Zeptatology. Alright. Is it not on blue? It's not on... Shoot! God dang it, the last recording wasn't on my microphone. Unless it was, because I remember wait a minute. There's no way it wasn't on it. I wouldn't let that happen. Quit. Rejoin. File new movie recording. It's not showing up. Where the heck did it go? I see sound... What? Go audio MIDI setup. It's not detecting. Why isn't this showing up? Blue microphone, show up, please. Please tell me that my previous recording was with my blue microphone. Because if it wasn't, then that is not good. Start the video. The positive half of this complex plane. That doesn't sound... Oh, God, I didn't record the last one with my blue microphone. Why is it just showing up? Oh, that's annoying. Okay. Oh, God. Shoot. Dang, man. That's not good. Where the heck is Blue Snowball? Oh, no. Oh, God. Let me unplug it. Let's see if it works with the even lower version. That is... Why isn't that working? Why aren't my beats showing up? Not my beats. I don't have beats. My Blue Snowball. It just doesn't exist anymore. Apparently, Blue Snowball doesn't exist. Why is that true? What are my voice settings on Discord? Ah, look at that. That also doesn't show up. Oh, haha. God. I just recorded an entire video without my blue snowball, but my blue snowball was in my hand. Shoot. Wait, let me move it to... Okay, unplug it, plug that back in, plug that in there. Does that work? It shows that it's on, but it's not showing up. New movie recording. Switch. Oh, now nothing's showing up. Not even the Logitech camera. So does the Logitech need the USB 3? Is it confused? Okay, there's Logitech. Was it because this thing wasn't plugged in all the way? It's there! It's there now! What happened? Something weird happened. Alright, don't turn off autofocus because autofocus is awful. Wow, okay, let's see if it was at the beginning. Start the video. It's in reverse. Wait, let me...
Actually, it's between negative pi over 2 and pi over 2, which is not all of...
Please tell me the audio is good. Oh, good. Okay, it sounds like it was recorded with the blue. Thank God. Thank God. Whew. Okay, let's do a wrap it up on tensors and vector spaces. Alright, I'll start with the axioms of vector spaces. That's usually the thing you start off with. So you start off, given a field, you have scalar multiplication and vector addition. These are the axioms. And I list out the axioms, then I define the dual vector space. Then I can define tensors. Although usually you don't define it that way. Okay. I'll define tensors as multidimensional arrays on p copies of the vector space, q copies of the covector space. Or the dual vector space, not covector space. Alright. Shoot, that didn't work. I'll say axiom of choice is equivalent to the fact that vector spaces always have a basis. Then I'll define a co-basis. Okay. Okay. This is going to be a good wrap it up. I have a feeling. I'm doing it completely on a whim. Oh, okay. Hopefully, the other audio is going to sound the same as this audio. Also, are my headphones still connected? Where did my headphones go? Please someone tell me. Okay, I found them. And they're not connected, it's fine. Alright. In this video, I'll be introducing tensors, vector spaces, and dual vector spaces on general fields. So if we have a field K under addition and multiplication, then a vector space on K is going to be a set V with an operational call circle plus and an operational call circle operation. And circle plus will take in two elements of the vector space set and send it to another element of the vector space set. And this multiplication will take in some element from the field and some element from the vector space and send it to an element of the vector space. And they have a series of axioms. And I'm just going to rip off Friedrich Schiller right now because he has a great mnemonic, and it's Connie Adu. Looks like that. C means commutative. V plus, shoot. So the Connie part is for addition, and the ado part is for multiplication. So now the C means it's commutative. So V circle plus W is equal to W circle plus V. And so this is the operation on two elements of the vector space. A stands for associativity. So V circle plus W circle plus, I'll go Z, is equal to V circle plus quantity W circle plus Z. N means neutral element, which I actually hate how that sounds, but what it just means is that there exists a zero element. So there is a zero element of the vector space, meaning that V circle plus 0 is equal to V for any element of the vector space. I means that there is an identity. Shoot, that's not what that meant. No, yeah. Shoot, I could have done a much better definition. I'm going to get rid of that. So I'm going with a much better definition. Alright, now the things we need for this to be a vector space. 1, V under circle plus is a binary operation on V, is an abelian group. 2, there are two types of distribution between scalar multiplication and addition. If I have V, so there's two different types of distributed, oh my god. 2 is that this multiplication is distributive, meaning that if I have some element of the field, and I scalar multiply that with some other element of the field, scalar multiplied with V, is equal to K times K prime, and this is within the field, scalar multiply V. Now I'm going to call circle multiply scalar multiply, obviously. 3 is that there's two types of distributive properties. If I have K, a scalar multiply V circle plus W, that is equal to K scalar multiply V circle plus K scalar multiply W. And there's one more type of distributive property. If I have, shoot, what was I going to do? Okay, I remember. If I have K plus K prime, and this is within the field, and I scalar multiply that with with V, then I can get K scalar multiply V circle plus K prime scalar multiply V. So no matter which one you're adding with, scalar multiply distributes. think that's it. Oh no, there's one more. And the last property is that 1 scalar multiply v is equal to v for every single element of the vector space v. These are the axioms for a vector space over a field K. Now, the thing about a vector space is that they can have a basis. And what a basis is a collection of elements v alpha, for alpha an element of some index set j, and we have it that for every v an element of the vector space, there exists a finite collection. There exists a finite number of v alpha, so v alpha I for I equals 1 to n, and a collection of elements from the field, which I'll call k alpha I for I equals 1 to n, such that v is equal to the sum from I equals 1 to n of k alpha I scalar multiply v alpha I. So for every single, so for a vector, there are a finite number of basis elements and a finite number of scalars, which v is a linear combination of. So that's your standard definition of basis for the real numbers as well. So this is just extending it so that we can have infinite dimensional vector spaces, and so that we can have it on general fields. All right. Covectors, dual vector space. Now, what we can define are linear maps. So a linear map between two vector spaces, v and w, and v and w are vector spaces over the same field K. This is called linear if we have it that phi of v circle plus w is equal to phi of v circle plus on whatever the domain is, on whatever the codomain is, circle plus phi of w, and that phi of k scalar multiply v is equal to k scalar multiplication on the codomain phi of v. We have those two properties for linear maps. And what we can do is define the linear maps between v and the underlying field k. Because k is a vector space over itself, what we define is that scalar multiplication is just normal multiplication. So by that fact, a field is a vector space over itself. So Ham between v and k is the set of linear maps phi from v to k. Alright, so this is the set of linear maps, which I'll write a little squiggle over the arrow if it's linear. So all linear maps between the vector space and the field it's over. Which I will, instead of calling it Ham vk, I'll call it v star, the dual vector space. I should introduce Ham before. Okay. Alright, now what we define is that the Ham set between two vector spaces v and w is equal to the set of all linear maps between v and w. And I'm going to write a little tilde over the arrow if it is a linear map. Alright. Fun fact, a field is a vector space over itself. What we define is the circle addition between two elements of the field is just normal addition on the field, and that scalar multiplication between two elements on the field is just normal multiplication. So a field is a vector space over itself. And so what we can do is the Hom set between V and its underlying field. So if V is a vector space over K, we can take the Hom set between V and K. Now, instead of writing it like this, I'm going to call this V star. And it's called the dual vector space on V. Now the thing is that V star, so we have all linear maps, which I'll represent by psi, between V star and the underlying set K. Shoot. Now V star is also a vector space. What we define is scalar multiplication on a phi. We have to apply this to some vector, because this is a linear map, remember? And what we define it to be is K scalar multiply phi of V. So that's obvious, and then phi plus psi of V is equal to phi of V circle plus psi of V. It's that simple. Alright. You can check that this obeys the axioms as well. And so because V star is a vector space, we can take V star star. Now the thing about V star star is it's practically equivalent to just V. Because let's say we have some map, psi, or let's say we have some map, phi, which takes you from V star down to the field. Then I can create a correspondence to some vector V and this. So for every vector V, I'll send this to the map phi by defining phi applied to some covector, to some element of the dual vector space, phi, and I'll define that just be phi of V. So this defines a new map. For every single vector, there is a linear map from V star to K, where you just apply the elements of V star, where you just apply the vector to the, where you just take the input and apply that to the vector. So, and that is a canonical homomorphism between V star star and V. Now we can define what a tensor is. And a tensor is a linear map, T, which takes you from V Cartesian product up to V Cartesian product V star up to V star. And it'll send that down to your field K. So right here, we're going to have P copies of V, and we're going to have Q copies of V star. Shoot, I might have this backwards. Tensor. V star. Okay, yeah, I had it backwards. And what a tensor is it's just a map which takes in a bunch of covectors, so a bunch of elements from the dual vector space, and a bunch of vectors from the normal vector space. And it will send it to an element of the field. And it's just a linear map. And if there are P copies of covectors and Q copies of vectors, we call T a PQ tensor. And this is a linear map between those, meaning it's linear in each slot. All right. And now tensors will have components. So tensors will have components I1 to IN, J1 to J, I1 to IP, J1 to JQ. Whew. This is not a good recording. The marker's wearing out. I'm just gonna salvage it from this. And that's it. Okay, I have to re-record that. What made you interested in math as opposed to science? Math's cooler. You don't have to do actual stuff. You can do whatever you want. That's why I like math. Ugh, okay. Oof. I should probably redo both recordings just to make sure that I got the best take out of them. So I'll allow myself to re-record the complex loci because I don't think I did too good with it. And I'll go ahead and plug all my things in. And I'll clean off the board. The board's disgusting. And I'll get a new marker. Okay. Good. It's not gonna put out subpar videos. Guten. Oh shoot, what was it? Ugh. Ugh. Shoot. I need my paper towels. Let me go get some. Ugh. And actually I should probably prioritize because actually I don't even need to unplug this. It's a USB right there. So I'll just have 10 things plugged into my gosh darn MacBook at the same time. Zoop, zap, zippity, zippity. There we go. Shoot. There. Alright. Let me go get paper towels. Welcome back to cleaning my dirty whiteboard. Zoop. Whew. Okay. 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 It's not a good recording, and I need some new markers. This one's broken. Yeah, I remember that. So I can't tell whether that one's full or not. It's too risky, so I'm not even gonna bother. Okay. A good, classic black marker. Classic, absolute classic of the genre. New movie recording. Let's make sure that's actual. Oh, are you kidding me? The settings keep resetting every time. Okay. Advanced settings. Turn off auto zoom. There we go. Ooh. We're gonna redo the first recording so that it doesn't suck. I forgot what I was gonna say during the intro. Guten Morgen. Guten Morgen.
Guten Morgen, liebe Mathematiker.
Guten Morgen, liebe Mathematiker. Okay. Ooh. Guten Morgen, liebe Mathematiker. Yes, I took that off of Google Translate, and screw you, Flammable Maths. Screw you. Anyway, in this video, I'll be introducing complex magnitude and complex loci. So the first concept is of complex magnitude. So we usually write it with absolute value signs, and what it represents is the distance between a complex number and the origin. So if we have the complex plane, and I have just some random number, a plus bi. So it has real component A, it has imaginary component B. So if I project, so right here is A. So if I draw a line straight down, that's A. And if I draw a line straight across, right there is B. Now, if I'm going to take the distance between that and the origin, it's going to be the length of that line right there. And you may notice that right here is a right triangle. Recording stop. Try again. Why did that happen? Stop opening it up. iTunes. Delete. File. New movie recording. For some reason Logitech webcam no longer an option. Okay, blue snowball is still plugged in. Now I have to reset all my settings on the Logitech webcam for like the 5th time. Stop opening up iTunes. Why is Logitech webcam only a... Oh my god. Why is it only a gosh darn stupid? Oh my god. Please work. Don't trust. Make it Logitech. Why is it a microphone? It's not a microphone. Okay, let's unplug my phone from here. Let me plug this back in. Logitech. Oh my god. This happened when I first got it. I don't remember what I did to fix it. New movie recording. Oh, there it is. All right, zoom in. Oh, that looks really good. Turn off autofocus. Save. Okay. We have to erase the board again. Okay. Let's go. Guten Morgen, liebe... shoot. Guten Morgen, liebe Mathematiker. Yes, I stole that off of Google Translate. And yes, screw you, flammable mass. Screw you. Anyway, in this video, I'll be introducing complex magnitude and complex loci. So, the first thing I'm going to introduce is complex magnitude. We usually write this with little absolute value signs. And what it represents is the distance between a complex number and the origin. So if I have the complex plane, looks like this, and I have some random complex number, a plus bi. This means that if I draw a line down, this right here is A, the point A on the real line. And if I draw it across like that, that means this right here is the point B on the imaginary line. Now if I wanted to do the distance between that and the origin, I take the length of that line right there, if I drew it right. Now you may notice that it's a right triangle, like that. Now what are the lengths of its legs? Well, by the fact that I know this length right here, the distance between A and the origin is just A. So the length of that leg is A. Now, I can use the same logic here and get the length of this leg to be B. And because this is a rectangle, I can move the length B over here. So the two lengths are A and B. Those are the legs of the right triangle. And then you may recognize, now obviously if we have a right triangle, we're going to use the Pythagorean theorem. So if I call the hypotenuse C, and this is the length we want to find, and we know A and B, use the Pythagorean theorem. A squared plus B squared, this is what we know. C squared, this is what we want to know. Pythagorean theorem, these are equal to each other. And then I just take the square root of both sides, and I get C equals the square root of A squared plus B squared. And by the fact that A squared plus B squared, A squared is always positive, or non-negative, B squared is always non-negative. And so there's no way that C squared, and now we're only going to take the positive solution because lengths can't be negative. And so if Z is A plus BI, we determine that its magnitude is the square root of A squared plus B squared. That is straight from the Pythagorean theorem. Now the other property of a complex number is something called its argument, which is basically its angle. So if I have the complex number, if I have the complex plane, and I have just some random point, then I draw the line to it, like that. Whatever this angle right here is, that is its argument. That theta right there. So if I instead had a complex number right here, so that right there is the complex number, I draw the line out from the origin. This angle right here, which is bigger than 180 degrees, is going to be its argument. And the special property about it is if I draw the same right triangle I did before, so one length's B, the other is A, the angle is theta, I can do the tangent inverse of theta, and I will get B over A. Shoot, I did that the wrong way around. if I take the tangent of theta, straight from the definition of tangent, TOA, opposite over adjacent, I get b over a, meaning that theta is equal to tangent inverse of b over a. Now this comes with some asterisks, because really, this only works for theta. This comes with some asterisks because this only works for theta between negative pi over 2 and pi over 2. Which is this portion of the complex plane. And you might notice that this one right here is not within that portion. To get all other values of theta, what you do is you take tangent inverse of b over a and you add pi. So for this quadrant of the complex plane, for those two quadrants of the complex plane, you take tangent inverse of b over a and you just add pi. And that will make it so that we have this value for the tangent, you add pi, and then you get the actual theta for it. All right, so now let's look at complex loci. Now with complex loci, you write all complex z such that, and then you write something there. And you can visualize, and you can write this mathematically as the set, which is represented by little curly brackets, of all z, an element, so this little epsilon character means an element of the set capital C, such that, you write a little bar, something else. So this means every z an element of C such that something else. All right, let's take an example. So I'm going to write it out. So all complex z such that the magnitude of z is equal to 1. And if I'm writing this in set builder notation, this is all z, which is complex, such that the magnitude of z is equal to 1. And the way, all right, let's visualize this set. If I have the complex plane, the magnitude of some complex number is the distance between that and the origin. And we fix that to be 1. So let's say this one is 1 away from the origin, this one is 1 away from the origin, this one is 1 away, this one is 1 away, this one, 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 like that. Now all of those are 1 away from the origin. And you can probably already guess what it's going to be, and it's probably better than a guess. It's a circle, because this is the set of all points which is 1 away from the origin, a constant distance from the origin, which is how you define a circle. So this is a circle, and so the loci of points whose magnitudes is, the loci of points whose magnitude is 1 is a circle of radius 1. And we can generalize this. The magnitude of z minus z naught, where z naught is some constant complex number, is equal to some r. This will create a circle centered at z naught, because if you remember from pre-calculus, subtracting off by a value translates it to that value. So this is a translation by z naught, and it will have a radius of r. Right? Because the magnitude is fixed at r. So this is a circle of radius r centered at z naught. And we can do this with argument. Now that's pretty cool. Now what if we set argument to a fixed amount? So argument of z is equal to pi over 4, for instance. The way I'd write this is the set of all z, an element of the complex numbers, such that the argument of z is equal to pi over 4. So this is the set of complex numbers whose angle to the origin is pi over 4. So let's draw out a point who has an angle of pi over 4, like that. And now this point has it, this point has it, this point has an angle of that, this point has an angle like that. It's just a line. But note that it's not a geometric line, it's a ray actually. So this is a ray because this is a ray and it does not include the origin. That's because the origin doesn't have an argument because it's tangent inverse of 0 over 0, which you can't even take the limit of. And so it does not include the origin and it doesn't include anything before it. Because imagine, all the things before it, this stuff that would complete the line, look at its angle. It's that angle, which is not pi over 4. It's 5 pi over 4. And fun fact, 5 pi over 4 is not the same as pi over 4. So this is a ray, not including its endpoint. And in general, if I have the argument of z translated to z naught equals some constant theta, it will look like this. We move it to z naught, and if we have the angle theta relative to z naught, it'll be the ray not including z naught. So it'll be that ray. So that's what these two loci mean. All right, let's do some more complex examples. Now I'm going to take some time to prove a very important property of the complex norm. And what you write is that the norm of z times w is equal to the norm of z times the norm of w. That is the theorem I'm going to prove right now. So let's say we have the magnitude of